All right, here we go with the sound waves video. I'm going to try to make this one a little faster than the last ones have been. So our essential questions, still the same thing. What is sound? How does it travel? How do the physical properties of a medium affect the speed of sound? What properties of waves affect what we hear? And then the Doppler effect is something we're going to talk about too. So sound itself is a vibration that travels through the air or other media. When these vibrations reach the air near your ears, you hear the sound. So sound waves are energy, just like any other wave we've talked about, going through a medium. So remember, that's what it travels through. It could be a solid, a liquid, or a gas, without the particles of the medium traveling along. So if you look at the picture, it shows whatever is making the noise. I think it's just a speaker in this case. And it makes the molecules of whatever it is, probably air, vibrate. So here we have our compression where it pushes, and then the rarefaction, kind of like how a slinky bounces back and forth, it makes it vibrate. But the particles stay where they are. They're not really moving. The energy is really moving. And it's a longitudinal wave. So it's a source of energy forcing the matter to vibrate in the medium. Remember, matter is what stuff is. It makes it up. Back and forth pushes the particles together, which makes a compression, moves it apart, making a rarefaction where it's farther apart. I'm going to keep going. Remember, you can pause whenever you need to. The medium is whatever the sound wave has to travel through. So gas, air is the one that's usually the most common, liquid, and solid. We talked about how in outer space there's no molecules, so they can't compress and come apart or rarefy, so sound can't travel through outer space. And that's called a vacuum, if you remember from the video. So the speed of sound depends on what the medium is. And we've talked a little bit about this. So the elasticity of it, like how elastic it is, the density of it, how many molecules are all packed in there, and the temperature, so how fast those molecules are moving. So at room temperature, so just a basic room, what it's normally at, sound travels through the air at about 342 meters per second. So 342 meters is actually about 1,000 feet a second. So if you look over at the chart, it kind of gives us some ideas of what gases, liquids, and solids, the different speeds. So you can see that air speeds are only in the 300s. Liquids, depending on whether it's fresh or salt water, have more molecules. If it's salt water, will be faster. That's like 1,500 meters per second. And then solids are the fastest of all, where it's 4,000 to 5,000, depending on how dense the material is. So how fast the sound will travel. So elasticity is like elastic, like a rubber band. So the ability of something to bounce back. So solid materials are more elastic than liquids or gases are, because the particles are really close together, right? So they just vibrate back and forth in the same spot that they're in. They don't have to move around because they're all right next to each other. So it allows a wave to move a lot faster. Density is how much matter there is in it. So that is going to depend on how close those particles or molecules, that's the same thing, particles or molecules of the substance are in the medium. So if it's something, we're talking about two different types of solids, like this table back here, get back there. We see that, wood and glass are both a solid, but glass is more dense. So it's going to move through it faster. So density is going to matter here too, not just whether it's a medium or a gas or a liquid or a solid, sorry. And then temperature matters too. If you think back to last year, we learned about how temperature affects how molecules move. Remember, so if something is warmer, molecules move around in it a lot faster. Think back to when we put food coloring in warm water and in cold water, which was an experiment we did last year, that the food coloring in the warm water mixed up a lot faster because the molecules are moving around on their own. So if something is cooler, sound is going to travel slower in it because the molecules don't move around on their own as much. If molecules are already moving around in something that's really fast, then they're going to vibrate faster and hit each other faster to spread that sound around. So that is going to depend on the volume and the intensity of our sound waves. But we also have properties of sound waves, which we've talked a little bit about. So we've got intensity, loudness, frequency, and pitch. So loudness is what you're actually hearing, right? Intensity is a little different, but it also has to do with loudness. So this is volume, really. That's what we're talking about here. And we've already talked about how it's measured in decibels. And this answers some of your guys' questions. We have a range of what normal decibel things are in everyday life. So we can't hear below 0. Breathing is about 10 decibels. We've got a loud radio is about 80, and at that point it becomes unsafe for our ears. So a subway is really loud, 100 decibels. A jet plane taking off is 120. We get up to gunshots at 130, and you know you're supposed to wear ear protection when you were shooting a gun. Or a metal concert is really loud. But average noise is about 50 decibels. Frequency, we've talked about how that's the number of waves or the number of vibrations that occur per second passing a point. And wavelength has a relationship with that. It's measured in hertz. So 50 hertz is equal to 50 vibrations in 1 second. So on this picture here, which one of these waves has the greatest frequency? Which one is going to have the most waves passing a point in 1 second? It's going to be this bottom one because that has the shortest wavelength, distance between those crests. So we're going to have a lot more waves passing by. So if we counted in 1 second how many waves were passing by, if this were moving, that would be how many hertz it was. And pitch has to do with frequency, how high or low it is. So a high frequency wave is going to have a high pitch. A low frequency wave is going to have a low pitch. So like a young girl is going to have a squeaky high pitched voice, but an older guy is going to have a low pitched voice because it's a lot deeper. It all depends on the frequency of the waves that are created. Remember, pause this, go back if you need to. The Doppler effect is something you guys have heard, but you just didn't know what the name of it was. So the change in frequency that it sounds like to our ears, that there's a change in frequency as a wave source is moving compared to wherever we are. So if you have a sound that's moving towards you, the waves seem to increase. The frequency seems to increase, so it seems to get higher and higher. So think about if you're like standing there and you hear an ambulance or a police siren coming towards you. It seems to be getting higher in frequency and pitch. But as it starts to move away from you, it starts to get a lot lower, and the frequency and pitch starts to decrease. So I just cut this off. I'm going to make sure I explained it. It's just like an ambulance. If it's coming towards you, it sounds like it's getting higher. As it goes away from you, it starts to sound like it's getting lower. And that's just called the Doppler effect or the Doppler shift. And it's all depending on where you are in relation to where the noise is coming from. It's not necessarily that it actually is changing frequency. It just sounds like it is. So it's called the Doppler effect. And I will show you what the video of this is in class, and you'll be able to hear it. All right. So that's the end of that one. I did make it a little bit shorter this time. So I hope you guys got what you needed out of it. Go back to anything that you need to write down more of, pause it, whatever, watch it again. But have a good night, and I'll see you in class.